That's okay. Thank you. So this is work done on the PRAC award. So thanks to NSF for that. Evolution of the small galaxy population is what I'm going to talk about. This is a collaborative work with a cast of thousands. Not only we have the N-Body shop at the University of Washington, and former members of the N-Body shop are now spread throughout the world, but we also collaborate with the Parallel Programming Lab here at the University of Illinois, that's led by Sanjay Kale, and a number of his graduate students and research programmers have helped us considerably with this project. So Ludwig gave a great overview of structure formation yesterday, so I'm just going to highlight a couple things. The image I have here is an image of the cosmic microwave background, a snapshot of the universe when it was only 380,000 years old. This is temperature fluctuations. And the thing to note is that first, the angular scale of these fluctuations is determined, as you probably know, by the total energy density of the universe. That is the dark energy, is what we call it. And then the amplitude, delta T over T, is basically specified by the amount of dark matter. Okay? And so this is telling, although it's actual photons, it's telling us a lot about the dark universe. Now, our theory of galaxy formation is that gravitational instability will take these small, 1 part in 10 to the 5 fluctuations, they will collapse under their own self-gravity and make galaxies, things that look like that. Now, if we're going to measure, say, the large-scale structure of the universe using these things, then we need to understand a little bit more about dark matter. So certainly the overall rotation curve is determined by the fact that it sits in a dark matter halo, but a lot of the visual impression you get here is due to baryonic physics, right? So there's obviously the gas. In the midst of gas is condensation of dust. And of course, everything is being lit up by stars, which are made of baryons. So the focus here is that baryons are important. Of course, they're important for other reasons. Some of my best friends are baryons. Okay? But my point is, we need to understand the baryonic physics, in particular, the star formation physics. Star formation. Who understands star formation? All right, it's really difficult. All right, so first there is the gravitational instabilities, but magnetic fields play a role, radiative transfer, stars form where the molecules happen. You need to understand the large-scale structure of the galaxy because the large-scale motions are driving, part of the driving of the turbulence. Turbulence is also being driven by, where is he? The supernova that we're just talked about. And these scales, you know, in order to do this kind of physics and cosmology, I think we're talking not exascale, we're talking zetascale simulations. Okay, so we need some way to tackle this in cosmological simulations. And just to give you a visual, all right? So that previous picture was like 20 kiloparsecs across. Here's a picture 4 parsecs across, showing the velocity structure. These the colors are bins of a couple kilometers per second. Velocity structure of star-forming gas. All right, so there's no way we're going to get that kind of scale yet. Okay, well, until we get our zeta scale computer, we're not going to get that kind of resolution in a cosmological simulation. So what do? So here's our strategy. We need as much resolution as we can get, okay, given current technology. On the large-scale structure side, we need to have a simulation volume that's roughly 20 megaparsecs, and that's kind of a minimum because it's from those kinds of scales that tidal torques can spin up our galaxy. That's where the rotation of the galaxy comes from. So that's sort of our, on the large scale side, but so we want to try to adopt resolution to a galaxy so we can get down to the sub-kiloparsec scales. In particular, we have giant molecular clouds, hundreds of parsecs, slightly smaller. If we can resolve those, then we have some idea what the spatial location of star formation is. But we can't do all that radiative transfer stuff, so we have a subgrid model where we recognize, okay, we don't know all the details, but we do know the stars form in high-density environments. We do know that the supernova that we just discussed about, well, that star formation is not an efficient process. And so feedback both from young stars, supernova, are regulating star formation. Ludwig talked about this yesterday. We need some prescriptions to handle the fact that we have a multi-phase medium and be able to handle, I called it the same thing he did, the overcooling problem, because you can't resolve that medium. So we have pieces of this in a star formation model and a feedback model that covers these 2 points. And just to make the point that the baryons are important even for the dark matter. So this is a result, I meant to put, this is Governadel and Ponson. But if you consider a dark matter halo or dark matter particle circulating some baryons in the middle, and the baryons go supernova, the dark matter particle loses some of its binding energy and its orbit increases. And certainly the baryons can recondense, but the dark matter is still left at a larger orbit than it was before. So what is happening is that the baryons are actually affecting the orbits of the dark matter. And this whole process, it's rinse and repeat. Okay? It happens many times over so that you can smooth out dark matter profiles. And just some results on this. All right, so the solid line is predictions from dark matter models. This is a mass of a galaxy and concentration, where more concentration is down and more core central density is up. Green circles are dark matter only simulations. If you include the effect of baryons, you get these red crosses, so more core dark matter profiles. And the blue, of course, are the observations. So including the baryons is how we can explain the density profiles of observed galaxies. So again, emphasizing the point of you've got to go down to these scales to get the baryon physics. So that motivates our Blue Waters project. Bill isn't here. We could use this slide, and I'm sure you have good slides. So we could come up. Yeah. But the volume here that I'm talking about is a bit smaller than what Ludwig was talking about yesterday. About the same as yours, okay? Because, all right, we need 25 megaparsecs for the tidal torques, but we want as high a resolution as possible. And so that's the trade-off here. The particular goal is to compare with Hubble Space Telescope data. There's a number of observing programs where they're trying to study galaxies as they're forming in a high redshift universe. And so we want to understand the physical properties of those galaxies that are being observed and connect them to the galaxies here and now. So that's the overall focus of our Blue Waters project. And just, we've run this Pathfinder simulation where basically 1/10 of our ultimate resolution with just 2 billion particles. We have force resolution. We'd like to get better, but and then we have it's a SPH simulation. The SPH forces are slightly harder, and in this volume, you have an example here. I'm zooming in to the volume. You see there's a little disk galaxy. Okay, so there's hundreds of these in the volume. Here's where I'd show the movie. You can see all the supernova going off as the disk rotates. It's cool stuff. But we have hundreds of those which we can study the dynamics and make observational simulated observations to compare with HST data. So that's what we have. We've just finished. Lauren Anderson, who's here, has been analyzing this simulation, comparing the luminosity function of galaxies. So this is, again, it's astronomer thing, so it's backwards. Okay, so bright galaxies over here, dim galaxies are over there. Here's observations from HST data. The gray area is where we have to think a little harder about radiative transfer. So although it doesn't quite match up here, we're kind of okay. What we're really concerned about is what's happening at the faint end. And the question is, are there enough galaxies at the faint end to produce the photons that will change the universe from neutral to ionized? So understanding the physical state of the universe at these redshifts is what our next paper is going to be about, right? Now, I wanted to talk a little bit about how we do the simulations and our collaboration with the Palo Programming Lab. They have this language they call Charm++, C++-based runtime system. And the idea here is that you over-decompose your problem into many more domains than you have processors, and the runtime system takes care of placing them on processors to do the load balancing, and it also, by doing that, you're able to overlap computation with communication. So you decompose into the objects, the runtime maps them onto the processors, and you get all these features. So load balancing, your objects get mapped onto disk. That's called a checkpoint. And so a lot of nice features we can use. So we've developed this code. We call it Changa for Charm N-Body Gravity Solver. It's an SPH plus N-Body code. So lots of features. I wanted to focus on the baryonic features. We have this star formation model now based on the molecular gas, because stars seem to form where the molecular gas is. Feedback, formation of supermassive black holes. We had a talk about that 2 talks ago. And yes, and regulating star formation via feedback. Just an example of how Charm can increase the utilization of your cluster. So this is processor utilization up to 100%. Right, I've got to calculate gravity. I've got to calculate hydrodynamics. Charm, I've got the gravity happening in blue. I've got the hydrodynamics happening in green, and we have that nasty communication happening in black and red. And so you can see how Charm is able to overlap communication. This is getting the long-range forces from gravity with the computation, which is in blue. Little bit of a load balance problem here, but very good utilization by overlapping the various stages of the computation. They have done a good job in scaling our code out to 500,000 cores on Blue Waters. This is with 12 billion and 24 billion particles. This is a strong scaling result. And you see that the parallel efficiency is about 95% at 500,000 cores, which is pretty impressive. But this is a uniform simulation. What's really hard, that's kind of easy, okay? Again, Ludwig talked about this. Load balancing in a highly clustered simulation is much more difficult. You have big load imbalances depending on where you're in a cluster or not. You also have communication imbalance. And furthermore, you don't want to run all your particles at the same time step. Thank you. If you're in a cluster, your dynamical time is much shorter than if you're in the void. And so you want to multi-step your simulation. And so let me just talk about the load imbalance challenge there. So here's an image where each point is not a particle, it's a domain. Okay, so I have 1 million computational domains, and they're colored by the CPU load. Okay, so you see that if you're in a cluster, it's a lot harder to calculate gravity for, if you think about it, for reasonably obvious reasons. And so distributing this load across processors is the challenge, and this is what the Charm++ runtime buys us. Furthermore, if you're multi-stepping, your load distributions are crazy. Okay, so here's a uniform simulation where each domain, a distribution of loads, all right, nice Gaussian about the mean. Once you start multi-stepping, you have lots of domains with nothing to do, and just a few domains that are doing the work. And so, all right, how do you handle that? One thing that has been implemented recently is basically a work stealing on the SMP node. So we take, here's one very overloaded PE. We have the other PE steal the load and significantly reduce the time to completion. And so with a clustered run, so this is now, it's dark matter only, but a redshift of 0. So present day universe, only 2 billion particles. We still get reasonable scaling only to 80% parallel efficiency at 130,000 cores. But what's more important is that if you do the multi-stepping, right, notice the difference. The parallel efficiency went down, but this blue curve is telling you about the time to completion. And so, yes, we're only getting 50% parallel utilization, but we're getting a factor of 2 or more in time to completion by using the multi-step method. Okay, so the simulation I was showing you is something that finished a couple of months ago, and we're analyzing it to produce some publications. What we're planning to use the rest of our allocation is to up the resolution by an order of magnitude in mass. And so that means that the force resolution can go down as well. And these things have just been implemented. The AGN feedback from supermassive black holes and molecule-based star formation is what we'll be planning to do starting this summer. And the kinds of things we get out of it, luminosity function, we have enough resolution, we can make simulated images using a radiate transfer program. We deconvolve it or convolve it with the HST scene to make simulation images that we can directly compare with observations here. I mentioned reionizing the universe. You need to understand the morphology of the galaxy if you're going to understand how many photons are coming out of the galaxy that are affecting the rest of the universe. And then, this point has been made before, these metal things are kind of important. It's what you and I are made of. And you need to understand the star formation history of the universe in order to understand how the metals are distributed throughout the galaxy to understand, say, where things like solar metallicity stars are being formed. And so the connection with the here and now through the mass metallicity relationship. And I will take questions.